Hello, everybody. Welcome to the month of April's UK Sky Talk. We're going to go ahead and get started here. And hello also to those of you who might be joining us online. So my name is Dr. Ryan Sanders. I'm a professor in the Department of Physics and Astronomy here. And I teach physics and astronomy courses to students here at the university. But I also do scientific research into the properties of distant galaxies in the universe. And over the past few years, we've been using the James Webb Space Telescope to expand this research. And as I'm going to talk about today, it's really allowed us to push back to some of the most distant galaxies in the universe and to some of the farthest reaches of the universe, which, as we'll talk about later, also pushes back to very far into the universe's past. Okay. So let's start with a very general overview of what the universe is made of. This pie chart here shows the makeup and percentage of different components of the total amount of energy and matter that is in the universe. As you can see here, the vast majority of it, about 2/3, is made up of something called dark energy. What dark energy is actually a huge mystery in science and in astronomy right now. It's some form of energy that is accelerating the rate at which our universe is expanding. But we do not know that much about this energy form. We see signatures of it. We do not know what it is or what's causing it. And it's a very active area of research and one which I'm not going to talk more about tonight. The next largest fraction, roughly a quarter of the energy and matter in the universe, is something called dark matter. And the name is very appropriate. Dark matter is matter that is present throughout the universe, but it only interacts with the force of gravity and it does not emit any light. So we cannot observe it through telescopes that detect light, which is how we observe most things in the night sky and in the distant universe. But it's there everywhere. It forms this sort of cosmic web structure that you can see pictured here from a computer simulation of dark matter in our universe. And the normal matter, things like galaxies and stars, they live in the densest parts of these filaments, this cosmic web that's formed by the dark matter. It basically forms the backbone, the structure that things like galaxies live on. And so then we get to the other just measly 5% of the energy and matter of the universe, which is what we would call ordinary matter. Things made of regular atoms, regular subatomic particles, protons, electrons, nuclei, atoms, things like people, planets, stars, galaxies. These are the things that we see when we turn our telescopes towards the sky. But as you can see, they only make up a small percentage of the total amount of energy and matter in the universe. But they're really interesting to us because they make up us and they make up the places that we live, right? And so it's very interesting to study these and to understand more about them, even though it's a small fraction of the total amount of stuff in our universe. And so we're going to focus on this small chunk that is ordinary matter and how we can learn about this, especially ordinary matter in stars and galaxies in the distant universe, as we'll talk about tonight. So first, I want to talk a little bit about the scale of the universe to give us a sense of kind of how big things are. We're going to talk both about the spatial scales of the universe, but also the time scale of the universe, because both are very different than what we experience in our everyday lives. So we're sitting here in a classroom on UK's campus. We could say it's something, it's some tens of feet across, maybe say approximately 50 feet across classroom, okay? If you were to zoom out to kind of the next largest structure, we're inside some building on campus. Maybe that's hundreds of feet across, okay? So we've moved up by a factor of 10 in size scale. We could step out by another factor of 10 and you get, roughly a mile, and that's about the size of UK's entire campus. So we've now moved up 100 times larger than the room that we're sitting in. So we can kind of do this and build up a scale of different distances. You go another factor of 10, you're talking about roughly the entire size of the city of Lexington. Another factor of about 30 or so, and that's about the size of the state of Kentucky. Move up by another factor of 10 or 20, and you've got about the size of the entire United States, which has a length from end to end of 2,000 or 3,000 miles. Move up another factor of a few, and you get roughly to the diameter of the Earth, which is about 8,000 miles. From there, we could jump up by a factor of 60 to get the Earth-Moon system. The Moon is about 250,000 miles from the Earth in its orbit. And so the diameter of the orbit of the Moon is about 500,000 miles across. And note that the Moon, that's the furthest distance that humans have ever traveled from the Earth. If we move up by a factor of about 400, we get to the size of the Earth's orbit around the Sun. The Earth orbits the Sun about 100 million miles in distance, or a diameter of about 200 million miles. And then we jump up by another factor of 30 or so, and we get the size of the entire solar system. From the Sun out to the most distant planet in the solar system, Neptune's orbit. The diameter of Neptune's orbit is about 6 billion miles, okay? So we started with the classroom. We've jumped up many, many times larger in size when you multiply all of these factors for each jump. So the takeaway there is if you combine all these factors, the solar system is about 600 billion times larger than the size of the room that we're in, okay? And that's kind of hard to wrap your head around, right? We can understand the size of the room, campus, cities, even the United States. But when we get to sizes for things in space, the size of things in the universe, star systems, or even larger systems, as we'll talk about, it's hard to wrap our mind around just how big things are, but the scales are really, really huge. So to move up from here, let's ask the question, how far away from the Sun and the solar system is the next closest star to us? Well, the next closest star is called Alpha Centauri. It's in the constellation Centaurus. It is the closest star system to the solar system, and it's 25 trillion miles away. That's 25 followed by 12 zeros. And if we compare this to, say, the radius of Neptune's orbit around the Sun at about 3 billion miles, this tells us that it's roughly 10,000 times further to travel from the Sun to Neptune than from the Sun to the next closest star, Alpha Centauri. So 25 trillion miles is kind of an impossible distance for our human minds to really understand in a basic sense based on what we see in everyday life. You can also see that measuring distances in miles is kind of tough because the numbers become really, really big. This is to the closest star, but we live in a galaxy of billions of stars, right? And so the vast majority of them are much, much further away even than this. So how do we measure distances when we talk about the vast distances across our universe? Well, we can use light as a measuring stick, and in particular, the speed that light travels as a measuring stick. So in physics, speed is defined as distance divided by time. It's how fast, if something moves across a certain distance, how much time did it take to cross that distance? So for example, if I drove up to Cincinnati, it's about 90 miles. If it took me an hour and a half to drive there, I can divide those two numbers and I can get that I must have driven at a speed of 60 miles an hour when I drove up to Cincinnati, right? Well, if we think about the speed of light, it's really, really fast. Really, really fast. Much faster than, anything that we have moving here on the Earth, like cars, planes, jets, even orbiting satellites. So light speed is about 186,000 miles per second. So every second, light travels 186,000 miles, okay? Or if you put this in miles per hour, it's about 700 million miles per hour, about 670 million miles per hour. And interestingly, light is, as far as we can tell, a cosmic speed limit. Nothing in the universe can travel faster than light. So this seems to be the speed limit for how fast things can travel in the universe. So light travels super fast, and that actually helps us because it makes it a good measuring stick to trace the very vast distances in the universe. So how do we use light speed as a measuring stick? Well, if you take that equation that defines speed as distance divided by time, we could rewrite this as distance equals speed multiplied by time. And a light year we can define as a unit of distance, which is how far light travels in 1 year, 365 days. Okay. So how long is a light year? How big is that distance in units that we use? Well, we can do just a really simple calculation, just a little bit of math, right? Not too hard. So 1 year, 365 days. We can multiply that by 24 hours per day to get almost 9,000 hours in a day. This is 525,600 minutes, like that song from the musical. And this is about 31 million seconds in a year, okay? And then if we take the speed of light, which is about 186,000 miles per second, we multiply it by the 31 million seconds in a year, then we get the distance of a light year, which is about 6 trillion miles. Okay, so you can see 1 light year, 6 trillion miles, it's a very large distance. And we can actually use this as a better measuring stick to measure distances in the vast universe. So this distance to the nearest star, that was about 25 trillion miles. If we measure it in light years, it's about 4.3 light years, okay? We could also measure smaller distances. If you imagine the sun to Neptune, that's about 4 light hours, meaning it takes light about 4 hours to travel from the sun to Neptune. So us to the nearest star, about 4 light years. So we can see the distances are very vast in the universe, and this is again to the closest star. The universe is much, much bigger than that. Let's also think about the time scale of the universe. The universe has been around for a while. It's pretty old. If we look at evidence that we have from different observations, from cosmology, we think that the universe is almost 14 billion years old, okay? So we can see that not only are the distances that we have in the universe very vast, but also the time scales are very, very long. So things changing as far as big events in the history of the universe, we're talking billions of years. And for many objects in astronomy, such as stars or planets, we measure their ages in millions and billions of years, which is, of course, much longer than human lifetimes, much longer than the record of human history. But these objects, they stay around for a while, and most of them, they change pretty slowly. And so looking at them on scales of millions and billions of years is how we handle things. So this map right here traces out some of the main events that happen in the history of our universe. On the left is the beginning of our universe as we know it, the Big Bang. On the right is the present day, almost 14 billion years later, and a lot of stuff happened in the meantime. After the Big Bang, we think there was maybe 200 or 300 million years where there were no stars or galaxies in the universe. It was full of atoms, mostly hydrogen and helium atoms, but they hadn't assembled themselves into the structures that we see in the universe today, such as stars and galaxies and planets. So we think it took something maybe 200, 300 million years after the Big Bang before the first stars and the first galaxies formed. And then between then and the present day, which is, about 13.5 billion years, a lot of galaxies formed and changed over time and grew into the things that we have today, such as the Milky Way galaxy in which we live and other galaxies that we see around us in the nearby universe, as well as the stars and the planetary systems inside of those galaxies. But this introduces an interesting question. If the universe spans such a large time scale, billions and billions of years, how can we look into the past history of the universe and learn about what happened in the past history? How can we learn how something like the Milky Way galaxy in which we live, how it might have formed over billions of years to become the home that we have in the cosmos today? Well, light, once again, treats us very well for this. So because light travels at a finite speed, again, it's about 186,000 miles per second, it means that when we look at objects that are very far away, it takes some time for the light to travel from that object to us on the Earth where we can see it. And the longer the distances the light has to travel, the longer it takes the light to cross space and reach us. And so light actually acts as a cosmic time machine. It allows us to see light from distant stars and galaxies, but we actually get pictures of them when we observe their light on the Earth or in our telescopes on or near the Earth as they existed in the past. So how does this work? Let's take our example of Alpha Centauri, the closest star to us. It's about 4.3 light years away. That means when light leaves Alpha Centauri, it takes about 4 years to cross space and reach the Earth. So that means if we snap a photo of Alpha Centauri from Earth right at this moment tonight, that light left the star Alpha Centauri 4 years in the past. And so that means we're basically getting a snapshot of what the star looked like, not in the present day at this moment, but what it looked like 4 years in the past. And if we look at objects that are further and further away, we get glimpses of the universe as it existed further and further back into the past. So let's think about how we can use this by thinking about the time that it takes light to travel from different objects. So the sun is about 100 million miles from the Earth, and it takes light about 8 minutes to travel from the sun to the Earth. So every time we see the sun in the sky, it's actually a snapshot of the sun as it existed about 8 minutes in the past. Next closest star, we just looked at this. It takes about 4 years for light to travel. And so we see that next closest star as it existed 4 years ago, rather than right at this moment. Let's think about our galaxy, the Milky Way. This is kind of a schematic map of the spiral galaxy, the Milky Way that we live in. Our sun is not at the center of the galaxy. It's about halfway between the center and the edge. And the entire diameter of the Milky Way galaxy is roughly 100,000 light years across. So now we're looking at really longer timescales into the past. So if we think of, say, from the sun where we are, if we observe stars in the center of our galaxy, they're located about 26,000 light years away from us. So when we use a telescope to take an image of the center of the Milky Way galaxy, we're actually seeing those stars as they existed about 26,000 years in the past. Okay? So looking at objects within our galaxy is tracing hundreds or thousands of years into the past when we actually see the light from those objects. But we can go further away. The Milky Way's next door neighbor, the sort of next closest galaxy that's roughly the same size as the Milky Way, is called the Andromeda Galaxy. This is in the constellation Andromeda. And actually, if you're out in a dark site away from the city, it's possible to see this galaxy as a little smudge of light with your naked eye, even without a telescope. And if you have binoculars or a telescope, you can definitely see it if you get out away from the city in a dark site. So the Andromeda Galaxy is about 2.5 million light years away. And so when we take an image of it, for example, in this upper one, which is actually a photograph of the Andromeda Galaxy from the 1890s, which is amazing that they could see that much, well over 100 years ago. Or in the bottom with the Hubble Space Telescope, so a very modern picture, we're seeing a snapshot of that galaxy as it existed more than 2 million years in the past, right? So it's very, very interesting when we go to larger distances. But that's the next door neighbor galaxy, and there are, unknown billions of galaxies in the universe. So we can go much further away. We could go to, for example, the Virgo galaxy cluster. Galaxy clusters are like the downtown big urban cities of the universe, lots of galaxies living packed close together. This is the closest one to us. And it's about 65 million light years away. So we're peering more than 60 million years into the past if you look at the Virgo galaxy cluster. Or if we think about what the most distant known galaxy was, say in 1990, which is the year that the Hubble Space Telescope launched, that object was known to be about 12 billion light years away. And so then you're peering billions of years into the past, and actually a very large fraction back to the very origin of the universe and the first galaxies. Okay, so as we push to being able to see more distant objects, we push further into the past and we can learn more about the history of our universe. So why is it difficult to sort of push further and further back, closer to the first galaxies, closer to the Big Bang? Why are distant galaxies so hard to see? Well, there's 3 very, very simple reasons for this. 1, they're small. 2, they're faint. And 3, they can't be seen in visible or optical colors of light. Those are the colors of light that our eyeballs see. Okay, so let's walk through these. Let's talk about it. First, they're small. Okay, even though galaxies are physically very large, right? They're of order, roughly 10,000 light years across, tens of thousands of light years across for galaxies. If you put them billions of light years away from you, they look very small when you look up at the sky at them, okay? So to give us a scale here, here's an example. We've all seen the moon in the nighttime sky. The full moon is about half a degree in size. If you took a protractor and you measured like how big the angle was when you see the moon in the sky, it's about half a degree. This is roughly the size of your pinky held at arm's length, okay? If we think about distant galaxies, they're approximately 1/3600th of a degree in size. That's the size of an orange if that orange was sitting about 10 miles away from you, okay? So they're very, very tiny. So we need telescopes and instruments that can see very small things in order to see distant galaxies, okay? So that's one challenge. Two, they're faint, right? So we're all familiar with, if you have a light bulb, if you have a flashlight, if it's right up in your face, it's very bright, but the further away it gets from you, it gets dimmer, right? Well, brightness decreases as distance squared increases, okay? So what this means is that if you have a light bulb and you double the distance it is away from you, its brightness as you observe it will go down by a factor of 4. If you tripled its distance away from you, its brightness would go down by a factor of 9, okay? So for example, if we took the Andromeda galaxy, which is 2.5 million light years away, and we instead moved it to 10 billion light years away from us as if it was a very distant galaxy, it would be 16 million times fainter because of the difference in distance, okay? So you can see, to see very distant galaxies, we need to see millions of times fainter than to see things in the nearby universe or things that are in our own Milky Way galaxy. So that's a difficulty. And then finally, kind of the most complex of these, is that they can't be seen in visible colors of light, optical colors of light that are seen by our eyeballs. So these are our familiar colors of light, like the rainbow, red, orange, yellow, green, blue, purple. These are the things that our eyes see. These are colors of light that our eyes can detect. So it turns out that the color of light is encoded in something called wavelength. Some of you may have heard of the concept how light is an electromagnetic wave. It's made of alternating waves of an electric field and a magnetic field. You don't need to know the complexity of that entire topic. All you need to know is that shorter wavelengths of light correspond to different colors of light than longer wavelengths of light. So for example, blue light has a wavelength that we can measure with a certain measure of length or distance of about 400 nanometers. And a nanometer is 1/1000th of a meter. Red light has a wavelength of about 700 nanometers. But it turns out that there's a lot of other wavelengths of light besides just what our eyes can see. This figure at the bottom shows what we call the electromagnetic spectrum. These are all just light at different wavelengths. On the left, we have shorter wavelengths, and on the right, we have longer wavelengths. Kind of in the left middle, you see the visible, the rainbow of colors that our eyes normally see. If you go to longer wavelengths of light, we have infrared light. And if you go to even longer wavelengths of light, you have radio waves. Radio waves are light just traveling with very, very long wavelengths, okay? Radio waves like the ones that carry signal to the radio in your car. If you go to shorter wavelengths than the visible, you get to the ultraviolet or even to X-rays at even shorter. And those are the photons of light that allow us to use, for example, X-rays to view, the inside of your body at a doctor. So these other things, ultraviolet, infrared, X-ray, radio, you could think of them as other colors of light. They're just colors of light that we can't see, and they have very different wavelengths than the wavelengths that we can't see. So for example, infrared light, which is longer wavelength than what we can see, has wavelengths greater than 1,000 nanometers or greater than 1 micron. A micron is a fancy term for 1/1,000,000th of a meter, okay? So if we go to longer wavelengths than visible light, we get to infrared light. What does this have to do with distant galaxies? Well, it turns out that there is something that happens in our universe called cosmological redshift. And this is a result of the fact that our universe is expanding. So every second in time that our universe has existed, the space in our universe is expanding in size, okay? This is something that was discovered back around 1930 by the astronomer Edwin Hubble. And so we've known about it for almost 100 years, this expansion of the universe. So basically, it's similar to blowing up a balloon. As you blow up the balloon, the size of the surface of the balloon expands. What's happening to our universe is the 3D space is expanding in all directions over time. So remember the wavelength of light, which is a unit of length, right? A unit of distance. It determines the color of light. When light is emitted from a distant galaxy and it travels across space for a long time to reach us, the whole time it's traveling, the space that makes up the universe that it's traveling through is expanding in size. And so when the space stretches out, it stretches out distances, and wavelength of light is a unit of distance. And so as light travels through the space, space is expanding, it stretches out the wavelength of light for as long as it's traveling until it reaches our telescopes. So when light of a short wavelength leaves a distant galaxy, it takes a long time, maybe billions of years, to reach our telescopes, and it stretches out the wavelength of that light quite a lot. And so for very distant galaxies, what happens is that light that was emitted, say in the visible wavelength range or in the ultraviolet wavelength range, gets stretched out so much as the light travels across such a long distance, there's so much expansion happening, that we actually observe it as an infrared color photon by the time it reaches our telescopes. So because of that, if we want to look at the most distant galaxies, we can't look in the visible wavelength range that we're familiar with. And it causes other problems too, because actually many of the wavelengths of infrared light actually don't penetrate through our atmosphere and reach the ground. And so to reach them, we have to send telescopes into space. And so that's something that we've certainly done and has motivated the design of the James Webb Space Telescope. So now we arrive at JWST, the James Webb Space Telescope. This telescope launched on Christmas Day in 2021. What a fantastic Christmas gift. Here you can see some images of the rocket launch from French Guiana near the equator. And then in the top was sort of the final image of the telescope itself. You'll notice that this doesn't look a lot like the picture of the telescope I'm going to show you in the next slide as it exists now. It was all folded up to transport itself because after it launched, it traveled for about a month, 1 million miles away from Earth to its final destination where it's observing the universe. So it launched in 2021. It got all opened up and began taking scientific data on things in the universe in 2022. So we've had it around for about a few years. Contrast this with the Hubble Space Telescope that we've all probably heard of as well. That telescope launched in 1990, and so is over 30 years old. Okay, so it's really great to get a new telescope, nice shiny new telescope like this. It has a 6.5 meter diameter mirror, which is the part that collects light on the telescope. I'll talk about that more in a minute. It's optimized to observe at infrared wavelengths, so it observes infrared light. So it's really, really good and designed for observing galaxies in the distant universe because, again, if they emit light in the optical or ultraviolet, by the time it reaches our telescopes, it's been stretched out to infrared wavelengths. And it has many different scientific instruments on board that allow us to take images and data on objects in the universe to learn about them. So let's look at this a little bit more. On the left-hand side here, you have a diagram showing the location where JWST is sitting. The Hubble Space Telescope actually orbits the Earth just a few hundred miles above the surface of the Earth, so it's relatively close to us. JWST, in contrast, is sitting at a point that's 1 million miles away from us. That's about 4 times further than the distance from the Earth to the Moon. It's at this point called L2 that sits directly opposite the Earth from the Sun. So it's in an orbit where it always stays on the direct opposite side of the Earth from the Sun. So that's where JWST is sitting. On the right-hand side, you see a picture of what the telescope actually looks like now that it's out there. So when it launched, that last image we saw of JWST as it left the rocket, it was all folded up into a little cube. Once it got out to its position, it spent a few months slowly unfolding and assembling all these pieces to see the picture you see here. So there's a couple important things here. One is this big gold hexagonal shaped structure. That's the primary mirror of the telescope. That's the part that's the most important. It collects the light from distant galaxies and allows us to see it. The bigger the primary mirror, the fainter objects you can see, and also the smaller details you can see, finer details. So this is great for distant galaxies, right? They're small, they're faint, and we can't observe them in optical wavelengths. So JWST has a big mirror. It can observe faint things, it can observe small things. And it's designed to work at infrared wavelengths. And in fact, the reason that's gold, those mirror pieces are actually plated in gold because gold is highly reflective at infrared wavelengths. So it's designed to observe in the infrared. It satisfies all the criteria we need to see distant galaxies. So light from distant galaxies will come in the front side. It'll hit that gold mirror. It'll bounce up to a second mirror in the front at the tip of that triangle. And then it'll bounce back into the telescope and go down to the scientific instruments where we can take, for example, images of the distant universe. It's important to keep all of this cold. And so this big silver sort of curved thing at the bottom is a sun shield that always keeps the rest of the telescope shaded so that it can stay cold, which helps it observe well at infrared wavelengths. So why send telescopes to space? There's some very practical reasons to do this. This is two images of the exact same galaxy. One is taken on the left with a telescope that's on the ground, so on Earth. And so to observe the galaxy from the ground, you have to look through the Earth's atmosphere. Now, the air in the atmosphere is always moving around. There's turbulence. It's always kind of moving around. We have wind happening, all sorts of stuff like that. And as photons of light travel from space through the Earth's atmosphere to our telescope, all of these small differences in temperature and density and all of these motions of the air, they actually blur out the image as the light travels to our telescope before we observe it. It's kind of like if you put a picture at the bottom of a swimming pool, it's going to be blurry and distorted compared to if you're holding it right in front of your face. So from the ground, we can only get a blurred out image of galaxies, but if you go to space, there's no air, there's no atmosphere in front of you between the photons that are coming from space, and so you don't get this blurring effect. So the right-hand image is the same galaxy, but pictured from the Hubble Space Telescope, which is in space above the atmosphere, and you can see how much clearer the image is, how many smaller and finer details that you can see, and it really highlights a reason why we send telescopes to space. Now, why is the James Webb Space Telescope better than the Hubble Space Telescope for viewing these distant galaxies? Well, for telescopes, size is really important. The bigger the mirror on your telescope, the more photons of light you can collect and the fainter objects you can see. The other thing that the size of the mirror does is the bigger the size of the mirror, the smaller, finer details you can see in the object that you're observing. So it allows you to see smaller things in clearer detail. So Hubble's primary mirror was about 2.4 meters or 8 feet in diameter. JWST's mirror is 6.5 meters, which is about 21 feet. So it's almost 3 times larger in diameter than Hubble's mirror. And the light collecting power goes as the diameter of the radius squared. Okay? So if it's roughly 3 times bigger mirror than Hubble, it can actually collect roughly 9 times more photons than Hubble. In addition, JWST's mirror, like I said, is gold coated to specifically be optimized for infrared wavelengths. It is physically larger than Hubble. So on the left, you have a picture of Hubble. Its physical size is roughly the size of a school bus. On the right-hand side, you have JWST, and including the sun shield and everything, it's roughly the size of a tennis court. So that gives you some scale of the actual physical size of these things. And so here's a great example, just putting it to work, of why JWST works better due to the size difference. Also due to the fact that, again, Hubble's been up there since the 90s. It was upgraded with different instruments a few times, but it's still much older technology than JWST as well. So this is an observation of a galaxy cluster, the same galaxy cluster. On the left is the Hubble image, and on the right is the JWST image. And so you can immediately see in the JWST image, you can see many more galaxies, you can see many times more fainter things, and you can see sharper, crisper details than in the Hubble image. So this just goes to show us the power of having this newer, bigger, and specially built for the infrared telescope in James Webb. So now let's take a look at some of the things that JWST has seen. And we're going to start pretty close to home, and then we're going to very quickly move very, very far away from home. So this is an image of Jupiter, right? So the largest planet in our solar system, taken with JWST at infrared wavelengths. So you may have seen pictures of Jupiter in optical wavelengths. It's kind of a tannish brownish color with some whites mixed in. Has a big circular storm called the Great Red Spot. This is at infrared wavelengths where we've colored different infrared wavelengths with different visible colors so that we can actually see the image with our eye. And what you can see is we can see lots of cool details about clouds and wind movement. We can see that big storm on the bottom right-hand side. You can also see there's these really cool red glows, or at least red colored in this image, on the top and bottom on the north and south pole of Jupiter. You wouldn't really be able to see that in a visible light image of Jupiter, but those are actually what we call aurora. This is like the aurora borealis on the Earth, where particles from the solar wind that comes off the sun get caught in the magnetic field of Jupiter, curl around and hit its poles, and it makes this interesting light show. So we can see the aurora on Jupiter with JWST. We can move further away in our own galaxy, about 400 light years away from the Earth. And JWST has been able to, in this system, for example, directly take an image of a planet orbiting another star. So the light from the star would normally be thousands of times brighter than the light from the planet that you're trying to see. But you can use special techniques to block out the light from the star. So where this white star image is in these pictures is actually the location of the star the planet is orbiting around. And then you can see this bright spot next to it is actually this planet. It's a very large planet. It's actually several times larger than the mass of Jupiter. But JWST was able to image this planet orbiting another star. If we move a little further away, say a couple thousand light years away, we can move to something called the Ring Nebula that's still within our galaxy. This is actually a visible light image from the Hubble Space Telescope of the Ring Nebula. In this picture, you can see a sort of ring-shaped structure of different colored gas. This is gas that used to be inside of a star, and when that star died, it basically started blowing the outside parts of the star off, and this is sort of the remnants of a dead star is what this thing is, something called a planetary nebula. One day, probably 5 or 6 billion years in the future, something like this will be the future of our sun in the solar system when the sun reaches the end of its life. So that's in visible wavelengths with HST. And here it is in infrared wavelengths with James Webb, where you can see very different details. The HST image shows you this sort of hot and warm gas. Different colors correspond to different elements in the HST image. The JWST images shows us very different things. It shows us lots of sort of dense clumps and very detailed structure. This actually comes from a dust that's forming in the material that's around this dead star. So very, very beautiful image of the Ring Nebula there at infrared wavelengths. So now let's leave our galaxy and look at another galaxy that's about 30 million light years away. That seems like a long distance, but that's actually a nearby galaxy as far as the scale of the universe is concerned. So this is a galaxy called Messier 74. It is a spiral galaxy, much like our Milky Way, so it's got these big spiraling arms. If you view this in the visible, you would see, bright clusters of stars tracing out the spiral pattern of the arm. When you view this in the infrared with JWST, you see a picture like this, which looks really interesting. You kind of have this like honeycomb structure with different shells and then with kind of darker holes on the inside. So most of the bright parts you're seeing here are actually dust and gas in this galaxy. And then those holes are basically low density regions where many of them, they're the locations of past places where supernova explosions, which is what happened when stars die, they blew up and they kind of blew holes in different parts of these galaxies. So we can see that in this wonderful image of a relatively nearby galaxy, Messier 74. Go a little further away, about 10 times further. This is about 300 million light years away. This is a group of galaxies called Stephan's Quintet. It's what we call interacting or merging galaxies. So galaxies are very massive. Everything with mass has force of gravity affecting it. And so if galaxies get too close together, the gravity actually starts pulling them together, and they will eventually get pulled together and merge together and form one new, even bigger galaxy. This is a really cool situation where you have not one, but you have multiple galaxies all getting pulled together by gravity and merging together. And in fact, it's called the quintet, but actually only the four at the top are merging together, and the one at the bottom is actually not at the same distance. It just happens to be in the foreground along the line of sight when we look here. But the top ones are merging together. You can see their structure that used to be a nice, beautiful spiral has all been disturbed by this interaction. They're eventually going to form a much more massive, bigger galaxy when they merge together. Something like this is actually the future of the Milky Way. We talked about the Andromeda galaxy that was its next door neighbor, about 2.5 million light years away. Andromeda and the Milky Way are actually getting pulled together by their mutual gravity. And so at some point, billions of years in the future, they're actually going to combine together in a galaxy merger and form one newer, bigger galaxy, which for better or worse, some people have named Milkomeda, which doesn't really have a great ring to it. So, maybe in billions of years, whatever life forms are present can think of a better name for their home system. So now let's really start to go far, far away from our galaxy in the nearby universe. This is an image that was one of the first observations that JWST took after launch. It's of a galaxy cluster that has the not so interesting name SMACS 0723. But this galaxy cluster is almost 4 billion light years away from us. And so you see lots of galaxies, lots of different colors in this image. We also see some bright points of light that have these sort of spikes sticking out from them. The bright points of light that have the spikes are actually stars in our own Milky Way galaxy. They're just in front of the direction of this galaxy cluster. So they're not that far away. They're in the Milky Way. They just happen to be in front of it when we try to take a picture of the cluster in the background. The galaxy cluster galaxies themselves are actually the whiter colored galaxies, the ones that are relatively white and kind of round shaped. Those are galaxies that are in this cluster. But there's all these other interesting galaxies of different colors, and many of them you can see have kind of stretched out arc shapes. Those are actually in the background further away than this galaxy cluster, and those are quite interesting. So I can highlight some of these. For example, this picture on the right, zooming in on this one, you can see it's this big sort of arc shape, like a section of a circle. These are galaxies that are much further away than this cluster, but all of the matter that's in the cluster can actually do something really cool to the light coming from background galaxies called gravitational lensing, where it takes that light and it magnifies it and stretches it out. It's kind of like looking at a picture in a funhouse mirror that's going to kind of stretch and distort things. But it also makes galaxies brighter. So it makes it easier to see faint background galaxies if you have this gravitational lensing effect happening. So on the right, you can see this background galaxy has been stretched out into this big arc that's much larger than the size of the galaxy actually. It's been stretched out by magnification, kind of like a funhouse mirror. This one on the bottom left that I've shown is another gravitationally lensed galaxy, but it's much smaller, it's much more distant. All you can see is just this tiny little red dot smudge. It doesn't look very impressive, but it's actually a super, very, very far distant galaxy that we can see. Even though it's so faint, we've been able to see it because of the help of this gravitational lensing effect. So that galaxy in the lower left, that small red dot, is actually 13 billion light years away. So that's allowing us to see the universe when it was less than 1 billion years old after the Big Bang. So JWST has taken many very deep images that can see very, very faint galaxies very far away. Here's one of those deep imaging fields. This contains thousands and thousands of different galaxies in this image. Some of them are closer. You can see some of the bigger ones. But the vast majority of galaxies you see in this image are more than 9 billion light years away from us, and thus trace back into the first half of all of cosmic history, those 14 billion years since the Big Bang. How far has JWST seen at this point? Well, the record has changed many times for the most distant galaxy JWST has found. But the current record holder is this galaxy you see here that goes by the name of Jade's GSZ14. You can see we're not the best at choosing exciting names for things, but this is the most distant galaxy known. So this inset panel zooms in on this galaxy, JWST 14. Um, there's two colors in the inset image. There's a sort of whiter thing and then a redder colored thing. The whiter thing is actually a closer galaxy that by happenstance lies along the line of sight to the background galaxy. The most distant galaxy is actually just the red blob on the lower right. This galaxy is at a distance of 13.4 billion light years. And if you're doing the math, that means we're seeing this galaxy when the universe was only about 300 million years old. So JWST has allowed us to push back and see galaxies that are within that time frame where we think maybe the very first generations of galaxies and stars formed that ever existed in the universe, only 300 million years after the Big Bang. So if we go back to our sort of schematic history of the universe with the beginning of the universe on the left and the present day on the right, tracing almost 14 billion years, how far has JWST gotten us in pushing back towards the earliest parts of the universe? It's gotten us to about 300 million years after the Big Bang. Will we find things at even earlier times, at even longer distances with JWST? It's probably likely. You know, we're only 3 years into the lifetime of the telescope. We're going to have it for at least about 17 more years. There's a lot more to find. And we'll just have to wait and see what time gives us to how much further back in time we can actually find galaxies and we can trace earlier and earlier in the history of the universe with the James Webb Space Telescope. But despite that, as you can see, this telescope has revealed lots of new details of our universe, both nearby, even as nearby as inside our solar system, and in the furthest corners of the universe, billions and billions of light years away. So I'll go ahead and stop there. Thank you for listening tonight to the UK Sky Talk, and I am happy to take questions from anyone here and also from anyone who's joined us online. Yeah. Yeah. Yeah, that's a great question. So the question was, what what determined the size of JWST, that 6.5 meter diameter mirror? What limited it? So, of course, we'd like to always just build a bigger telescope because you collect more light. And in fact, the biggest optical and infrared telescopes we have on the ground right now have bigger mirrors than JWST. The biggest ones are about 10 meters in diameter compared to JWST's 6.5 meters, right? So that would collect much more light. But the issue is, as you've guessed, is being able to launch it on a rocket. And so the challenge, I mentioned how JWST had to be all folded up to fit into the payload bay of the rocket it was launched on. And the rocket it launched on could carry the largest payload of any rockets that existed at the time of launch. So the limitation was both the weight and just the size of something that could fit into a launch vehicle and go out there. So there are certainly plans to build ever larger space telescopes in the future, but in order to make those happen, we also need the rocket launch technology to get better as well. Yeah, so the hexagonal shape of the little pieces of the mirror um, does make it easier to fold, and it's also technology that's been used in other segmented mirrors on the ground. So, for example, the Keck telescopes, which are 10-meter telescopes in Hawaii, are made of 1 meter hexagonal segments. Yeah, so I think it's both the fact that it was, technology we knew how to use, also that it made the ability to fold the primary mirror up so that it could get smaller and fit inside the rocket. Yeah. Yeah. you're- Yes, that's a good question. So the question was like how small of planets have been seen by JWST, because the one I showed was, like a big planet, larger than Jupiter, which is the biggest planet we have in the solar system. Um, I do not know the exact number on this, but JWST is certainly looking at smaller planets. Um, and for some of those, it might not be directly imaging the planet, but with the spectrographs on JWST, it can actually take a special type of spectrum that can tell you about the material in the atmosphere of planets. This is actually a really cool thing where if a planet orbits in front of the starlight will pass through the atmosphere of the planet, and then we can see absorption if we take a spectrum of the star when the planet's passing in the front that can tell us about, for example, molecules that are present in the atmosphere of the planet. The hope is to do stuff like that to identify, for example, planets in the habitable zone that are Earth mass that have, water or different biomarker molecules. So you could find planets that are habitable or planets that might have molecules that could potentially be indicative of supportive life. So, yeah, but I don't know the exact number of how many, say, like towards Earth mass planets observed so far. Yeah. Uh, yeah. So you can see for like closer objects, say like Milky Way stars, you can see absorption for different molecules in the infrared. But if we look at the very high redshift galaxies, we can get absorption lines that are in the emitted in the ultraviolet, and we can see them at very high redshifts. Yeah, yeah. So it is possible. It's difficult, but it's possible. Yeah. Cool. So looking at this galaxy, like got an orange down all the way. Oh yeah, yeah. Yeah, so the orange thing, I managed to like, okay, you know, how far would you have to put it away for it to be like basically like kind of crazy. Like, yeah, yeah, it does. I mean, again, you're talking about, like see the size of the whole moon on the sky. You're talking about GWC's resolution is more like 0.1 arc seconds, so that's 20,000 times smaller than the full moon. Yeah. Like, the dust thing, yeah, it's really, it really is kind of amazing.